Hello everyone. In today's video tutorial, we are going to present several methods to apply screw preloading to a structure in Abaqus software using Abaqus Explicit. Although bolt preloading exists in Abaqus standard as a loading condition under the load module, it's not available in Explicit solver, and this is reasonable because when we tight a screw, it's let's say a quasi-static event and not a transient or a fast event where we want to capture the behavior of the structure in short periods of times, something that Explicit solver is designed to handle. Normally we could run a first static or quasi-static analysis using Abaqus standard, and after solving the bolt preloading time step, we could use the results as a pre-stressed condition to a subsequent step in Explicit solver. But maybe this is a little bit complex, so we are going to present some methods where we can apply the screw preloading in an explicit step and continue our analysis with Explicit solver. So I have created some models in Abaqus software, and let's start in presenting all the alternatives. So in this model that I have named as thread geometry, as you can see, I have included the geometry of the thread in my parts, both internal and external thread. And if I create an instance including all these three parts, I have prepared my model in the CAD software, and I have assembled it properly, so the coils of the thread have a small clearance between them, and as you may see, I have created a gap as a cross section in the screw, in my screw. I will explain why I did that. So let's create our material. We will go fast by having only one material, steel, and we are going to include linear properties. Young modulus 200 gigapascals, 0.3 Poisson ratio, and the density, because we will do it in Explicit solver, say 45 minus, we are working with millimeters. Yes, create the section, perfect, and let's assign the section. Okay, perfect. Let's measure our parts. So here the geometry is complex because we include the geometry of the thread, so we can go with tetrahedral elements. Go fast. We can use, let's say, 2.5 as an average size, but we can make it a little bit finer, close the threads, the region of the thread. So select this and make it 0.5 here. Perfect. Explicit. let's make it linear elements, perfect. So let's continue to this next part. Five. Perfect. And okay, leave it as it is. Tetra elements. Perfect. So what's next? We'll create a dynamic explicit step, and we are going to use the mass scaling option because we don't care about inertia effect at this time step, and it will help us speed up the step of the screw preloading. So let's assign a large time step of -7. And let's make it not 1 second, but 50 milliseconds. Okay, perfect. Let's ask for the mass, percentage for the mass scaling. I usually the frequency for the results. Let's make it X unit of time. Perfect. The same. I ask for results every 1 millisecond. And now what we're going to do is let's have a section, cross section. We'll create a reference point here and here. We'll create coupling constraints, and we couple this reference point with the one cross section of the screw. We'll do the same for the bottom. Perfect. And we are going to create a connector between these 2 points. We'll create a translator connector with available only the degree of freedom on the one axis of the local coordinate system of the connector. Okay, okay. And we're going to create a loading as a connector force. Create sets. This is the only connector we have. Okay, I forgot to mention to create an amplitude. So let's create first a smooth step of 1.50 milliseconds. amplitude 1. Now I can create the load connector force. Connector, we'll use minus because we want to apply the axial force for the screw preloading, and feasible resonant value for an M8 screw, let's say 7.5 kilonewton. You can see the arrows here. Perfect. We are going to fix our structure on the bottom. Dismiss. Perfect. And what we will do next? We'll create a second step, again explicit, 0.5, 5 milliseconds. Masking conditions, we have to change it, because if we don't change it, we will follow from the previous step the same value. So now we'll put a smaller time increment. Okay, perfect. We'll create again an amplitude, again a smooth amplitude. Now we have only 5 milliseconds, and we are going to create a loading as a pressure for the step 2 to capture if our structure is well fixed with the screw preloading on the first step. So here, let's say a magnitude of 5,000 newtons, amplitude 2, total here, and to loading one boundary condition. And what we have to do next is that we will lock the velocity of the connector during the second step. Set wire 0. Perfect. And here in the load manager, we have to deactivate the connector force and make it exist only on the first step. Perfect. So our model is ready. You have to create an analysis, job 1, and you can click submit. I have already run the analysis, and I will show you the result after. Okay, let's see them now. Open. You can see the preloading of the screw, and here is a second step with the force coming in the x-axis. Oh, perfect. Nice. Okay, let's continue with the second method. It's a little bit simplified when we don't include the geometry of the thread, and we have a simplified screw. And let's create here the assembly. And you can see it better. Perfect. So here we have a simplified screw without including the thread, the geometry of the thread, and we'll do the same job here. We will create a reference point, perfect. We will create a constraint with the surface of this, the cross section of the screw, perfect. Again for the second surface, we'll do the same job. Perfect. We will create a connector, again translator, perfect. Okay, let's do the same job. Elastic. Three. Nine. Create section. Side section. Perfect. Let's mesh the parts. This can be easily meshed with hexane elements, but let's go with tetra elements like the other parts. Okay. Okay. So the only difference is that since we do not include the thread geometry, we have to create an additional constraint between the screw region and the threaded region of the other parts, a tie constraint. So this, hold the shift key to select both surface, and now we can see the other purple, and here we have the tie constraint. This is the only difference compared to the previous model for our solution, and we have to follow the same procedure and create the boundary condition as previously, and fixed our structure, and we have create Okay, yes, we haven't created the steps, the time steps. Again, dynamic explicit, 50 milliseconds, a large time step for the first step. Perfect. Second time step, 5 milliseconds, another. Time increment, perfect. I will leave as is the field and history output request. Okay, something I missed from the previous analysis, then we have to include interaction properties. We have to assign a friction between the parts. I didn't do that in previously, but you must do that because we have 3 different parts. You can create general contact for explicit. And you have to create general contact for explicit here. No, step 1. Step 1, perfect. I missed that. Okay, nice. Again, the amplitudes, smooth steps, 0, 0, 50 milliseconds, 1, amplitude 1, amplitude 2, perfect. Loading for the connector force again. Select the connector, the same force, amplitude 1, perfect. And let's create also this in the step 2, the pressure condition. Come on. Total force 5 kilonewtons, amplitude 2, perfect. Again, the boundary, the lock the connector for the second step, step 2. Zero, yes, and don't forget to deactivate the connector force for the second step. I think we're okay. Create the job, second job. And I will show you also the results from the analysis that I had run with the course. This one. Okay. You can see the 2 steps. Okay guys, so now I will also show you the most simplified method to do a preloading. Maybe this make your structure more rigid, is without using at all a screw, and just create some conditions. You have only these 2 parts, and you can create 2 reference points. Let's create this and this, and you create the constraints, the first with the upper part with this surface, and the second with the bottom part. With this surface. Perfectly. So again, you have to create a connector, a translator. Perfect. And again, you have to do the same procedure. Again, contact, don't forget it. And normal, perfect. General contact, nice. And you have to do the same procedure for the loading and the boundary condition, and mesh the part, run the analysis. I will show you quickly the results, course 2, but you have to have in mind, but because the results could be your structure with very rigid, because you have constrained all the degrees of freedom with the reference point and the constraints, the coupling constraints. So you can see the force and a small movement of the upper part. So guys, I hope you found my tutorial informative and you liked my video, and stay tuned for next video. Bye bye, thank you for watching.